This is Spotlight from All Things Photonics, featuring intimate sit-down conversations with preeminent figures in our industry. Unscripted, timely, and topical, this series shines the spotlight on industry-leading changemakers from all corners of the photonics landscape, from the gateways of progress to the most impactful challenges of our time.
Today's episode is brought to you by Hamamatsu Corporation, a leading manufacturer of devices for the generation and measurement of infrared, visible, UV light, and X-rays. Hamamatsu is dedicated to the advancement of photonics through extensive research and offers specialized systems for select applications. Visit hamamatsu.com to learn more.
So much talk in the photonics community today is centered around things like quantum or AI or maybe laser fusion. While it's easy to see why there's so much excitement around these topics, it's important to remember that the materials required to drive tech in these areas may actually be thousands of years old. Glass surrounds us, but its significance is often downplayed. While it literally provides the window to our future, its role in fiber and other optical systems should not be understated. Material science, specifically glass, enables functions that many assume are the work of electronics. And with the advent of hollow-core fiber, glass could play an even bigger role in future advancements. John Ballato, professor of material science and engineering at Clemson University, knows the importance of glass. Across his more than 200 published papers, his research often focuses on new optical materials and structures for photonic and optoelectronic applications. In this Spotlight conversation, he shares his thoughts on what's driving a resurgence in glass and its future in our industry. Joining me today is John Ballato, a professor of material science and engineering, professor of electrical and computer engineering at Clemson. John, thank you so much for giving us the time.
Oh, my pleasure. Thank you, Joe.
I wanted to talk today about glass, an established technology, but what are some of the new areas of progress and what are some of the applications that are driving advancements in this area? In your experience, what other widely used optical materials, polymers, for example, are influencing the growth trajectory of optical glasses?
Yeah, it's a great question because seems like so many aspects of optical materials are enjoying something of a renaissance these days, and there are a few pieces I think that are driving it. But you started, I think, where the best place to start is, which is glass, right? So, humankind has used glass for thousands of years, right? 5,000-6,000 years. Going back to Egyptian and Greek times, where people again dug sand out of the earth and they used soda and calcium, seashells and things like that to make glass, and we've gotten better and better and better and better at it. And then of course fast forward thousands of years later, glass is the enabler of so much that we do in optics, and clearly, it is the backbone of all of the optical fiber that surrounds the world and brings all sorts of communications and social media and e-commerce and all those things. But what's fascinating about it is, as old and as established as glass is, especially as relates to fiber, the demands that are placed on the glasses today that go into optical fibers, whether those are for communications and data comms, whether those are for directed energy and defense applications, for sensors, for medical, the reason that glass in particular is experiencing kind of this renewed attention is because the applications and the demands for those applications today are driving people to realize that fundamentally materials enable the performance of any system. right? In an optical system, you have a source that's making the light. You have a medium through which that light is transmitting, and then you have again some receivers or detectors on the other end that are processing what happened to the light along the way. And glass is integral to that middle place, where the light is actually interacting with its surroundings. And again, those demands are getting more and more stringent, right? We want more information, right? Our data communications, we want more information. We want it faster. We want it cheaper. We want to send it longer distances without any parasitic effects coming into play. Again, and that fundamentally is a interaction of the light and the glass through which it's going. With respect to high-powered things for, again, directed energy or cutting and manufacturing, cutting and welding, things like that. Again, more power, just raw power onto whatever the target is. But oftentimes in systems like that, it's the glass that's actually generating the light, right? It's a glass-based laser. It's a fiber laser. In some of those cases, the fiber is a little bit bigger than the size of your hair. And the amount of power, optical power, that is coursing down it, you divide the power by that small cross section, it's tens of thousands of times more intense than the surface of the sun. So, beginning to think about how on earth can this material that we have used for thousands of years and take for granted, quite honestly. I know it's glass. It's there it is. It's I'm looking through my window. It's glass. This optical fiber. 500 million kilometers of it are made every year. It's just glass. We'll just make another 500 million, and it's all the same. But it's not, right? So the applications of today, again, either it's high power or it's information capacity or it's distance or it's all sorts of other kind of more boutique things. They are forcing us to go back and understand just kind of fundamentally what happens when the light passes through this thing we call glass, and how do we make that transmission more clear, more efficient? How do we make the generation of light at different colors or at higher powers, or so it is a great time to be a material scientist, and specifically to be a glass scientist.
And talking about the appreciation of glass, the it just melted sand, fire, like, come on. But I think some people may be confusing. You talk about the light being generated from the glass, and maybe some people are confusing that with the electrical systems or something else. What do you say to those, or how do we enlighten those people that are really downplaying the importance of glass and the advancements that are being made with it?
So I'm trained as a glass scientist, right? So as you probably know, most of the technical community in photonics has usually a background that's in physics or in electrical engineering or something like this, maybe occasionally photonics. Very, very rarely is it in material science, and even more rarely is it in actually glass science. So that's a great question. Try to think of a world where, again, you try to think of a photonics world absent glass, right? You would have no windows, right? You would have no robust protection on your tablets and your phones, right? Those are glasses. On your displays, those are glasses. The fiber, again, that without which we essentially can't live, right? I'm trying to think of my kids without their social media or access to internet and things along those lines. All of those things are glass enabled, right? So even if you don't understand the fiber that is, in the walls or up on the foam pole or under the ocean, right? Even if you don't understand the glass piece or the fiber piece of that, everybody assumes today that data, again, enabled by glass, that data is as much of a utility as power, as water, as anything else, right? Electricity, right? So you can go anywhere, certainly in the developed world, and there are certain things you expect to have, right? You expect to have power, expect to have potable water, you expect to have, those types of modern conveniences. And the one that you can add to that now is the availability of data, and without glass, that doesn't exist. So so people like us wake up every morning thinking about all of those photonic systems whose performance is predicated, large or small, on the performance of the glass that's inside it. Right. Our job is to think about how is it that the periodic table, right, this chemical spice rack that nature gave us, how is it that we deploy that in ways to make that glass do more of the functions that the electronics you mentioned do today, right? Because again, if you think about this, or at least this is what we spend our time thinking about, there's always an electrical interface, right? You type on a keyboard, or you with your phone, or there's an electrical interface, and then there's optics, and then there's another electrical interface on the back end, right? And so there's stuff that the electronics do, there's stuff that the optics do, and then there's, again, stuff that the electronics do. One of these areas that's particularly, I think, exciting and having a moment that I think is going to just continue to grow and grow and grow is taking some of the functions that the electronics do on the front and the back end, and actually finding ways that the optics or the glass itself, the materials itself, can do some of those same functions. So integrating optoelectronics into the fiber, into the glass, things like that, making the system much more holistic, where the glass and the fiber, where the materials are playing multifunctional roles than they do today.
Very interesting. So are there other materials, or, we talk about the periodic table, or things that we should be looking out for that are going to be influencing the next stages for glass?
Yes. I think that's always going to be the case. One of the things I tend to think about and find fascinating is, again, periodic table, right? So you got nature gave you 100 things, right? I mean, there's more than 100, but
right,
there's roughly 100 that are not going to kill you, straight off, right? So we're going to not worry about the radioactive things and all that stuff. But there's about 100, and so then you begin saying, okay, well, if I have 100 things, how many permutations of those 100 different things are there? And that's virtually limitless, right? But at the end of the day, right, if we look out around us at all of the technologies, it still comes down to just a handful of stuff, right? All of our electronics are silicon, right? Maybe there's a little bit of germanium. Maybe there's some things that are like, gallium arsenide, or 2.6s, 3.5. Anyway, you got a few crystals, you got a bunch of different flavors of glass, you got a bunch of flavors of plastics, but at the end of the day, there's probably 20 to 30 materials. Again, some are metals, some are semiconductors, some are glasses, some are plastic. But there's 20, 30, 40 materials that represent 95, 98% of all the stuff that we use on a day-to-day basis, right? So that's just that's a nothing piece of the periodic table, right? So, but it is very, very hard to bring, kind of a new material to market in a big way, right? Academics love to, we made this much, we made something new, right? But it's this big, right? So we're going to publish our paper. We're going to move we're going to move one over on the periodic table. We're going to make it that much. And But anyway, so one of the reasons why you only have these 20, 30, 40, whatever kind of things that everything uses is because of that. They work. We've scaled them up. They're commercially successful. They're economically viable, right? So displacing them is hard. So unleashing the periodic table while it's a fanciful thing for us academics, it's not a practical thing. So what I think you're going to see, and I think you already are seeing some of this, is the integration of those existing things into common platforms. And again, you see this on a chip, right? You see more functionality. Chips used to be electrical, right? Well, now you have electronics and optics on chips, right? And you also have chips that are all optic, photonic, right? So this integration, this seamless integration of electronics and optics and optoelectronics and linear functions and nonlinear functions and computing, the chip is becoming more multifunctional and more multi-material, right? Because ultimately, again, it's the material that enables this. I think, again, in our world, which is fiber based, I think you see more of that in the fiber, right? So we think today the vast majority of fibers that we use are ones that are, there's a glass in the core, there's a glass in the cladding, there's a plastic protective layer, and there's another plastic protective layer. But you got two types of glass, two types of plastic, and you got then you make a cable, then you install the cable. Just like in the cables that are on the pole, that are under the ocean, that are in the buildings, those fiber cables have lots of different fibers, but they're all fibers. Where you begin to see a lot of interesting stuff going on, which is only, I think, going to grow in the future, is where the fiber, again, is doing more of the function. So you got glass for transmission of light. You got metals for transmission of electricity. You got semiconductors for doing optical functions, but in the form of a fiber. So bringing the chip functionality into the fiber. And again, you see, there's a lot of growth in things like wearable sensors, wearable fibers woven into uniforms. MIT's done a lot of this work in the past. It's just some wonderful things there, and in Asia as well. But this idea of integrating multiple materials into common platforms like a fiber, leveraging, what has been done on chip. I think that's one of the ways in which the chemistry of the periodic table and the physics of electronics and optics and photonics and optoelectronics, all of those begin to kind of merge into common platforms of chips and then fibers.
Today's episode is brought to you by LightPath Technologies. From concept through prototyping, volume production, and global distribution, LightPath has the optical and infrared imaging knowledge and manufacturing expertise to be your optics and thermal imaging solutions partner every step of the way. Visit lightpath.com to learn more.
And you mentioned optical fiber, and we talked about a bit of a renaissance for some glass technology. What is pushing the demand for the advancements in optical fibers? And, does it have to do with the increased demand for AI, calling for enhanced data speeds, and how that movement is impacting the growth trajectory of optical fiber enabled technologies?
I would say there are a few things that are pushing the demand for fiber. One is just the fact that so much of our existence is online today, right? Us having this conversation, it used to be on the phone, right? And now it's over, video. But again, social media and movies and video on demand. We teach classes, through Zoom and other web portals, e-commerce. Again, think of what your day would be like if you did not have a device, at the ready. So, and again, all of that is fiber enabled, not just enabled, but predicated, right? It doesn't exist if not for the fiber. And so there's more. There is more people. There's more usage. There are more applications that we feel the need every day to, as soon as we wake up, the first thing you almost always do is grab your phone. At least I do. But don't tell my kids that. But so much of modern society again, is predicated on the performance of these photonic networks. Again, the innermost workings of which are based on the glass. And so just that data segment, right, of photonics, again, more data fast. You want more of it. You want it faster. In other words, more bandwidth. You want it cheaper, right? You want all these things. You want greater connectivity. You want it instantaneous anywhere in the world you go, right? You're frustrated if you don't have Wi-Fi wherever you are, right? So that drives the 5G rollout is a big piece of this, right? You have fiber manufacturers that are standing up entirely new fiber fabrication facilities just to meet the demand for 5G. And after 5G there'll be 6G, and there'll be so we're not going from 5G back to 4G, right? We're going from 5 to 6 or 5 plus, whatever. So the data, just the data side in and of itself, demands further improvements in the fiber. There are more networks, right? We're there every so often you see a new subsea cable going in. Well, those fibers, you want lower loss, you want fewer repeaters, amplifiers, So again, all of that is baked in back at the science and engineering, the materials and the fabrication side. And again, that's just the data piece. Defense, security, those obviously are growing as all sorts of your viewers and listeners, are they know the global circumstances that we're in, and those aren't going away anytime soon. So defense and security is always going to be a requirement, and a lot of again, defense and security apparatus are moving to optics and photonics, right? Because again, for bandwidth reasons, for directed energy reasons, we're not going back to tin can and string, and that's a big place of this. Then again, you got energy, you got medicine, you have just again scientific research, astronomy, manufacturing and machining. Right, a lot of lasers there, not just automotive, but also aerospace. So manufacturing advanced structures, not just big structures like an airplane or a car, but even small. Many of the parts in your iPhone or your tablet, those are cut using lasers. So when we talk about all things photonics, there's the photonics that you see, but so much of photonics is oddly enough invisible to us, but it enables just stunning percentages of what we do and what we expect in our daily lives.
Yeah, you might not visibly see it in front of you, but you would certainly notice if it wasn't there.
Yeah, no, that's right. That's exactly right.
Mm-hmm. So let me ask now, how could new advancements in optical fiber provide a boost to the emerging field that we're hearing and seeing more about of photonic quantum computing?
Right. Quantum computing is interesting. To me, again, not as a physicist, not as a quantum person, because it seems as if everybody who talks about quantum computing and all things quantum, it means something different to every person you talk about. So the answer may depend on the specific sector that you're thinking about. But if you think about communications, right, the quantum computing is one thing, right, and that potentially enables these massive enhancements in the speed and the complexity of calculations, right? But again, the brain, right? The brain that is now this quantum computer that's going to do these marvelous things, whatever that calculation was that the quantum computer did or will do, that answer, that information has to come out and go to whomever asked the question of the quantum computer, right? And so the more those systems are used, and the more the availability of those responses are, and the better they are, and the quicker they are, and all of that is also going to drive the demand for more fiber, for better fiber. If the information from the quantum computer remains in some sort of optical quantum or quantum optic state, then the information being transmitted over that fiber is going to have to persist that state or those states. Or if they're coupled states and things along those lines, the fiber is going to have to get smarter, so that whatever information is whatever quantum information is encoded onto the light, onto those photons, that it persists further into the fiber or along that fiber-based network. So I think there's a good question as to whether the fiber, or to what extent the fibers that we make today that go into existing networks, to what extent are those up to the challenge moving forward for these types of networks and these types of systems and solutions. And it may be that requires, I don't know, it may be that for those specific systems and networks, that may be a different type of fiber. Yes, it will almost have to always be glass based, but maybe it's all glass, maybe it's hollow core, maybe it's some other thing through which the light is guided. But nonetheless, it will be glass enabled, just like they are today. But it may very well be something a little bit different than we're used to.
Yeah, it's fascinating. Everything moves so fast, and one advancement spurs another, because everything has to keep up with the systems. When you boost something here, you need to boost something elsewhere, and certainly, glass is going to be a cornerstone in keeping everything running. So let me ask you, I'm reading some reports, and there are experts predicting that the fiber optics market will reach more than $16 billion in the U.S. by 2032. What is driving this, increase in demand, and are there advances that might surprise some of our listeners in fields in healthcare, defense, industrial automation, kind of, et cetera?
Right. I think, again, I only see certain pieces of this, but it certainly seems that a large fragment of that market is communications, of course, data communications these days, and again, implementation of 5G over larger regional regions is one piece of that. The growth of data, the proliferation, I would argue, maybe of data centers, right, and just the glut of information that go into and come out of data centers is a piece of that. There's a staggering amount of fiber inside of data centers, right? Because fiber is not just, it does. Fiber is, of course, used for these long distance communications, right? But it is also central to communications within data centers as well. If you can do more of the rack to rack communications over a fiber, as opposed to wires or other types of connections, again, there are various bandwidth and speed, latency benefits that kind of accrue from doing that. So 5G and then subsequent 6G, and just bandwidth growth to those of us on the consumer side. Then you have the connectivity at a regional, national level, and then of course international, subsea level. And then as you see more wiring at the premise scale, as you see more wiring and fiber use inside of data centers and things along those lines, all of those are just kind of adding to the demand. And I think that's a lot of what you see in some of those numbers. Then to your other point about where do those things either leverage or are added to growth in other sectors. Yeah, I mean, again, the use of fibers as the actual, medium inside of a laser that is doing the work. So fiber lasers, fiber amplifiers, not just for telecom, but again, machining, manufacturing, defense, security, biomedicine, or medical applications. All of those segments are growing. They're generally small-ish compared to the data side. But within just the piece that is fiber, there are companies that your listeners would know of that you think about, oh, they do this, but when you kind of peek under the hood, they have not small investments in medical or not small investments in sensing and these other areas. So the data piece obviously gets a lot of visibility because of, again, our insatiable need for information on demand. But yes, medicine and sensing and security and manufacturing are all growing. So you have multiple market sectors, all of which are growing, even though they're growing at different rates.
Gotcha. And let me, in closing, kind of ask you, we know the photonics industry is expanding into all fields. It's a cornerstone right now, frankly, for a lot of the systems that we see all around us and those applications, healthcare, defense, everything. What is the state of fiber today and where everything stands? And do you see any big changes on the horizon, or is there something we should be looking out for as far as like a new trend or something to watch for?
I'll give you one because it's one that I've been thinking about. It is important to say, though, that there's again roughly half a billion with a B kilometers of optical fiber are manufactured globally every year, right? Which again is a staggering amount of material if you think about adding that up. And every year there are innovations. You just don't see it, right? Because it's in a cable, it's in a fiber, it's in a cable. It's but every year those fibers do get better. What's been really interesting, again, at least for me, from my perspective, are some of these advancements in things like the hollow core fibers. And I say it as a joke, but it really is true. As a glass scientist. Where again, I wake up and I'm thinking about glass and how to make the glass in a fiber better for whatever the application. It is counterintuitive and almost an anathema to me to say I can make a glass fiber better by removing the glass, right? I mean, and that's essentially what you're doing, right, with a hollow core fiber. My friends who do that for a living, I still remind them that even though there are holes in it, it's still what is there is still glass, and so it's glass enabled. But nonetheless, that has become fascinating to me, and it's still in the early stages, but investments by companies like Microsoft in buying a hollow core fiber company out of Southampton. When you see investments like that by companies like that being made, you're like, there's something to this, right? You don't make that type of investment if you really don't think the technology has such potential to jump past your competitors. And I will admit here that I was not an advocate in the early days, because again I'm a glass person, right? So I'm like, of course glass is better than no glass, but I've become I'm a convert, I guess you could say. I've gone from a antagonist to an enthusiast, and I am not just optimistic, but I am fascinated to see now that there is another tool in our toolbox, what again, fiber enables all this stuff. So the more types of practical fibers you have at your disposal, the more tools are in your toolbox. What can you build that you couldn't build before because of that new tool, right? That's what I'm very interested to keep an eye on and see where that goes.
Yeah, and we'll keep our eyes peeled too and see how hollow core makes its way into the field. John, thank you so much for giving us your time and having this conversation with us.
Oh, it's my pleasure. Thank you.